15.2 and 15.3, thin lenses and optical phenomena. The objectives here are to understand the difference between a converging and diverging lens and their applications, to determine the critical angle of an incident ray, and to identify total internal reflection and its applications, and then finally to discuss atmospheric refraction and dispersion. First, let's recall that when a light ray travels through a flat glass, it's bent as it enters, but then it's bent again as it exits. So remember that here's our normal, right? Let's draw a normal here. It hits the surface, and then you would think it would continue along the dotted line, but it bends toward the normal. It bends toward the normal because it slows down when it hits glass. But then it hits the next interface, which is going from glass to air, right here. Well, suddenly you would think that this would continue in this direction, but it bends away from the normal because it's going faster again. So what we end up having here is an example that the light ray that came in ends up being the same as the light ray that exits, right? Except they're just parallel. It's kind of like they're shifted over, shifted downward. So you don't really see any of this effect when light comes through glass because it gets bent, but then it gets bent back again. Now, to focus or change the direction of light, the surface needs to be curved, okay, so that all the rays can pinpoint on one final location called the focal point. And a surface like this is called a lens. A lens is really just a transparent object that refracts light and causes them to do two things. Either first, it could cause them to converge or cause them to diverge. So for example, a converging lens would be something like this. Here's the thickness of the lens. The light rays enter the lens in the front, and they're all bent. They're all bent toward what we call a focal point. And the focal point is on some location or at some location on the other side of the lens itself. So this is a converging lens, also sometimes known as a convex lens. And then a diverging lens, which happens to be also known as a concave lens, does the opposite. It takes these rays that are coming in parallel and it causes them to diverge or move apart from one another. And here the focal point is kind of confusing, but if you look at it, you would see there's actually a focal point back here, okay, behind where the image began. So this would be where the focal point is. But since it's a diverging lens, we're not even looking at where it's focusing in this case. We're just trying to diverge those rays. So what's important is that we notice that this is a diverging lens. Now let's take a look at an application of lenses, and the simplest example is to think of corrective eyewear, like glasses or contact lenses. In this case, and you could think of it either way, you could think of this right here as either contact lenses on the surface, or think of these as a piece of glass, like glasses somebody would wear. So you could be farsighted or you could be nearsighted. If you're farsighted, it means that you can see far. Okay, you can see far, but you can't see near. So again, farsighted means you can see far. Another word for farsighted is called hyperopia. And hyperopia has to do with your eyes. And in your eyes, what happens is that these light rays come in, they hit the lens on your eyes, and then they get the focus. But when you have hyperopia, the light rays focus too far away, all the way back here, instead of focusing on the retina right here where we'd like it to. So what you do is you put a converging lens in front of the actual lens of your eye. That's this lens right here. And this converging lens causes these rays to start to converge earlier. So since they converge earlier, they end up converging sooner, and they end up converging right on the retina itself. Okay, right on the retina itself. And for nearsighted, it's myopia. And with myopia, the rays converge too near to the lens. You want to converge further away back here. So you put a diverging lens in the front so that these rays diverge, so now they're spread apart further, and then when they converge at the end, they'll converge on the right spot. They won't converge so soon because they started being diverged first, and then they have to come back. Now again, the whole idea is that you want to have the ray focus on the actual retina back here. So when you're at the doctor's office and they're flipping through those slides and you're taking a look at your eyes and you look at your actual prescription, they're just changing the curvature of the lenses when they slide through them until they find the one that matches you and you say, oh, that looks the best. And that's the one that causes the rays to focus right on the actual retina. Let's take a look now at an example of an optical phenomena that we're going to discuss called total internal reflection. And what's happening here with total internal reflection is that the ray is being bent so much by the material that it's going into that it actually bends back into the original material. So let's take a look here. If I draw a normal in at all these locations, right, there's my first one. What I'll notice here is this. The angle right here, if this deviates from the normal, the incident ray is pretty small. But the angle that comes out is pretty big. Because again, when something moves from water, or a slow-moving medium, to air, like a fast-moving medium, this little angle becomes much bigger because it bends away from the normal. So if this were like, say, 20, this would be something bigger than 20 for sure. Same thing happens with these next few. If I draw normal in here, so these are all different light rays. Again, this is like one light ray. This is a completely different light ray. This is not dispersion. These are just different scenarios. Here, take a look at this angle. This angle might be like 30 degrees, but now look at this angle. This is almost like 70 degrees on this side. So the angle of refraction is so much greater than the angle of incidence that eventually this angle of refraction becomes 90 degrees. Instead of it being like 70 degrees here, you end up getting an angle of refraction of almost 90 degrees toward the end here. And this 90-degree angle of refraction causes what's called total internal reflection, which causes the light ray to be refracted at an angle where it exists only on the surface. And then if you go any further, so if you make this angle any bigger, so here's our critical angle right here between the normal and the light ray. This is the light ray that's called critical, that angle, because it causes this internal reflection. If your angle is larger than that, anything bigger than the critical angle here, so for example this angle here, this is bigger than this critical angle that was right here, it's going to cause the object or the ray not to only ride along the surface when it gets refracted, but be refracted back into the medium itself. So again, this occurs when you go from a slow-moving medium to a fast-moving medium only, because that angle of refraction has to be greater than 90 degrees for it to be reflected back into the surface. So this is called total internal reflection. And a good example of this is when you think of something like a diamond. When a diamond, light enters into the diamond from the air, it goes into the diamond, it goes to escape out of the diamond, but because the diamond has such a great end value, it's got a very low critical angle. And we'll see that in a moment that the critical angle is in the 20s, which means that any angle greater than 20 and less than 90 that's trying to escape, a light ray that's trying to escape at that angle, would be refracted back into the material itself because it's above that critical angle. So what we'll notice is that when the refracted ray is parallel to the surface boundary, like we looked at, remember once this ray becomes a high enough critical angle right here, right? This is our theta I. And once this angle here becomes large enough, it causes this light ray here to be refracted along the surface boundary. So it looks like this, right? That's what ends up happening. Which means that the refracted angle, here's the normal still. Here's the normal. Refracted angle is 90 degrees. The incident angle is whatever you had. This incident angle becomes what's called a critical angle when this occurs. So we replace this with theta C and say it's now called the critical angle. Because this angle, theta R, is equal to 90 degrees here. So what that does is, Snell's law gives us the following. Ni sine theta I equals Nr sine theta R. Well, Ni in this case is left alone, but sine of theta I, well, this is really just theta C now. The incident angle becomes critical after it exceeds a certain amount of degrees. So again, like something like maybe 20 degrees wouldn't cause this, but something greater than the critical angle. So if this were the critical angle, estimate say it's 40 degrees, all angles larger than 40 degrees with respect to the normal. So any rays coming in like this, or ray coming in like this, or like this, these are all angles bigger than 40, would all cause total internal reflection. So on the right hand side though, now we have Nr, and this is just the sine of 90. Okay, so determining the critical angle at that exact instant in time, this angle is 90. Eventually, this comes in even further. It comes back refracted and becomes more than 90, but that's when the angle exceeds the critical angle. But at the critical angle, it's exactly 90 degrees for refraction. So this simplifies the equation. It allows us to write Ni sine theta I equals Nr. Why is that? Well, that's because the sine of 90 is just 1. So now what we'd really like to do here is we'd like to solve for that critical angle theta C. So here's our critical angle right here. Let's go ahead and solve for the critical angle to see what it is. So divide by Ni, and we get sine theta C equals Nr over Ni. Then solving for theta C, the critical angle, we take the sine inverse of both sides. getting theta c equals the sine inverse of nr over ni. And this makes sense because remember, we're always moving from a medium that is slower moving to a faster moving medium, always for this to occur. It has to happen that way. And if you're moving from a slower moving medium, it means that the incident value is going to be greater. Remember, the greater the n value, the slower the material, or the ray moves in that material. So ni has got to always be greater than nr in these cases. And you'll notice that because you can't take the sine inverse of a number greater than 1 because of the range restriction of the sine function. So because you can't do sine inverse of something greater than 1, this denominator ni right here has to be bigger than the numerator nr, always. And that always makes sense because the incident material is slower moving, and thus it has a higher n value. So this would be like glass and air. Glass is 1.5, air is 1. So you'd have 1 over 1.5. Example 1 says to determine the critical angle for light traveling from diamond into air. So let's take a look. So we've got this diamond here, right? And it's shining. And the ray travels into the diamond, and now it wants to travel out of the diamond. And at a certain angle, it's going to come back into the diamond and cause total internal reflection instead of going out here in the air. We want to figure out what that angle is. So again, the incident material this time is diamond, because we're looking at the ray from when it's already in the diamond when it's trying to escape. The second or refracted, attempted to be refracted material is air. And finally, we're looking for our critical angle theta c in this problem. We know our formula says theta c equals sine inverse of nr over ni. So we do the sine inverse of 1 over 2.419, giving us 24.4 degrees. So this tells us that anything larger than 24.4 degrees will cause total internal reflection when it comes to a medium of slow moving to a faster moving medium. Now some applications of total internal reflection. For an example with fiber optics or light pipes. And the way fiber optics work are that light is guided along a simple fiber, or again known as a light pipe. But it's at such high angles compared to the normal. Right here's the normal right here. This is such a great angle. It's greater than the critical angle. And that causes this light to be reflected back into the light pipe. So even though these are clear and these are light pipes, no light is actually exiting here. And that's what's happening here with these devices, or these little like toys that kids used to play with. The light comes from the center, from the actual light source, travels through the light pipes, but you don't see any light along the pipes. You only see the light at the very end of the pipe. So the light comes out here. It starts here, travels all the way through here, and you see it only at the end. This is how fiber optic cables really work, or the basis of how they work. And finally, the last thing is called dispersion, which is the process of separating or refracting white light into its component wavelengths. And this is very similar to refraction because you're bending the light, but you're bending it in such a way that you get all of the different wavelengths out. And this type of internal reflection is what causes a prism to separate colors, or for water droplets to produce a rainbow. So when a rainbow is produced, the water droplets act as a prism, and this causes this dispersion.